Today we're going to finish Lesson 2 notes, sketching the graph of a polynomial function. So we left off with number 3. Number 3 is in standard form, it is not in factored form. Standard form is helpful for things like end behavior and the y-intercept, but it is not helpful to find the zeros. So I'm going to start by factoring x to the fourth minus 2x cubed minus 8x squared. So again, in order to find the zeros, you need this to be in factored form. I'm going to start by factoring out x squared. That's the greatest common factor. Left over is x squared minus 2x minus 8. And then I have to think to myself, what two factors multiply to equal 8 and negative 8, and the same two factors that add to equal negative 2. That would be negative 4, positive 2. X squared times x minus 4 times x plus 2. Okay, this here is our factored expression. And this one up here would be in standard form, just to review the different formats. Okay, I'm going to follow the same order that we did in the previous problems. So last class what we did was we started off looking at end behavior. Then we looked at x-intercepts. Then we found additional points between the x-intercepts, and we also found the y-intercept. Okay, you don't have to follow that order exactly. I tend to always go in the same order. You just have to make sure you have all these parts. All right, end behavior. So for the end behavior, you're always looking at the degree and the leading coefficient. And when you do that, you're looking at it in standard form. In the previous problems, we've had to find the power function, but this one's already in standard form. So here we can see that we have a degree of 4, which is an even number. And we have a leading coefficient that is positive. It would be 1. This tells us that as x approaches positive infinity, the function approaches positive infinity. And as x approaches negative infinity, the function is approaching positive infinity. That means both ends of your graph face up. And I'm going to sketch 2 arrows just to indicate that these are the final locations of your graph. Next, we're going to find x-intercepts. And with this, let's find the multiplicity and what happens at that point. Our first factor, x squared, that would be x equals 0 or 0, 0. This has a multiplicity of 2 because the exponent is 2, or that factor happens twice. And that tells us that on the graph it's going to turn at that point. Our next 0 is x minus 4 equals 0, therefore x equals 4. The intercept would be at 4, 0. Multiplicity is 1, and this would cross at that point. Our last 0 would be found by x plus 2 equals 0, therefore x equals negative 2. Negative 2, 0, multiplicity 1. it crosses at this point. If I come over here to the graph, I know I have to make room on my x-axis to fit up to the point 40. So I'm just going to sketch a couple tick marks, going up by increments of 1. I can plot a point at 0, 0. I can plot a point at 4, 0. And a point at negative 2, 0. Now I need to find points in between each one of these x-intercepts. So I need to find a point in between here and another point in between here. You can pick any x value to test, it just has to be somewhere in between. So I already tested points, and between these two here, I picked to test negative 1. And when I tested x equals negative 1, I substitute that back into the original equation, and my output was negative 5. Therefore, I have an extra point at negative 1, negative 5. My next additional point, I tested between here at 0 and positive 4. I chose to test x equals 2. When I substitute 2 back into the original function and I simplify, I end up with an answer of negative 32. Therefore, I have an additional point at positive 2, negative 32. And for the last step, I need to find the y-intercept. The y-intercept is found by substituting 0 in for x. When I test that in the original function, my output is 0, so my y-intercept is at 0, 0. Okay, so I need to fit these 3 points on the graph. Which means I need to fit down to negative 32 on the y-axis. Let's jump down by increments of 10. Remember, we're just sketching. The y-axis is increasing or decreasing by increments of 10. My first point is at negative 1, negative 5. That would be approximately right here. My next point is at 2, negative 32. That would be approximately here. And my y-intercept is at 0, 0, which is already graphed. So I'm going to start on the left side of my graph. I'm going to pay attention to multiplicity, and I'm going to make sure I touch all of my additional points. So I need to start facing up. I'm going to approach the 0 at negative 2, which my multiplicity says to cross. Come down, cross through that point, come down, go back up. I'm approaching the 0 at 0, which my multiplicity says to turn at that point. So I need to come down, I need to hit that point, turn at 0, head back down, make sure you touch your additional point, head back up where I'm crossing at 4, and I'm heading up forever. Make sure your ends of the graph match your end behavior. Make sure at every point the multiplicity matches with what we determined. So here we know that it's crossing. Here we know that the graph needs to turn or bounce. Here we know that the graph is crossing. Also, make sure when you're graphing that you touch all of your additional points. That's why you find them. Okay, your graph does not have to be perfect, it is just a sketch. For the last set of examples, we are asked to write a polynomial based on the graph that's given. So there's a few ways you can do this, or there's a few parts that you can use to do this. But I like to take a look at the end behavior, the number of turning points, and the zeros, as well as the y-intercept, and make sure all of that stuff matches by the time I write my final function. So the first thing that I want to notice is that there's 1, 2, 3, 4 turning points. So based on our description, the number of turning points is always one less than the degree. So that would be the minimum degree. Of course, there could be functions with a larger exponent that could potentially have 4 turning points. So I'm just going to make a note. We need to make sure this matches at the end, that we have 4 turning points. So again, minimum, degree of 5. I'm also going to make a note of the zeros. We have a 0 right here at -2. If the 0 is at -2 and it crosses through the graph, that tells us that the multiplicity would be 1. We have a 0 right here at x equals -1, also multiplicity of 1. A 0 at 0, multiplicity 1. A 0 at 1, multiplicity 1. And a 0 at 2, multiplicity 1. So these are the zeros. It's where the graph crosses the x-axis. Remember, if it had a multiplicity of 2 or an even multiplicity, it would bounce or turn at that point. That doesn't happen on any of these. So once I list my zeros, I'm going to write a potential function. Now this might not be your final answer, it's just a potential graph. I'm going to use all my zeros starting at x equals -2, and I'm going to write them as factors. If x equals -2, then the factor has to be x plus 2. That way when you set it equal to 0 and you solve, you get x equals -2. We have x minus 1. Oh, I just realized I made a mistake. Sorry, this should be -1. I know I said -1, but I wrote +1. All right, so x plus 1 would be that factor. We have a factor or a 0 at 0, so a factor of x plus 0, x minus 1, x minus 2. All right, we need to clean this part up. We would never write x plus 0 as a factor. That's just x. And typically we write x in front of the function. So I'm going to rewrite this function as f of x is equal to x multiplied by x plus 2 times x plus 1. We already moved this x, so we don't need to write that factor again. X minus 1 times x minus 2. Now we have to make sure the y-intercept is correct. So we're going to test the y-intercept, which is when x equals 0, and we're going to make sure that it comes out to be true. If it doesn't come out to be true, then we need to add a multiplier as what we could call our GCF. We need to add a multiplier in front of the function to make the y-intercept match. So testing f of 0 would give us 0 multiplied by 0 plus 2, multiplied by 0 plus 1, multiplied by 0 minus 1, multiplied by 0 minus 2. So this would be 0 times 2 times 1 times 1 times -1, times -2. But right here, no matter what, we're multiplying that by 0, so this comes out to be 0. Now, is our function showing that we have a y-intercept at x equals 0, y equals 0, or 0, 0? So check on the graph up here, and yes, this function does indicate that we have a y-intercept at 0, 0. So this worked out, this is good. That means this here is our final function. Okay, also check before we're done. I should have mentioned this before I highlighted my answer, but also check to make sure that your degree works. So we determined that the minimum degree is 5. That means if we had a power function, we would multiply all of our first terms together, x times x times x times x times x. That would give us x to the 5th plus whatever else. And yes, that means our minimum degree is 5 because the degree is 5. So that checks out. Based on what we know about turning points, this graph matches. Okay, so it might be tempting to just find the zeros and just write them down, but you do have to be careful because, for example, this next graph, the y-intercept is going to change your final answer. So you have to do all of the work that we did on the last problem. Quick note, we have 2 turning points. I'm sorry, we have 3 turning points. That tells us that it's going to be an even degree because both ends face down, so they face the same direction. The degree, or the minimum degree, would be 4. We know that because of the turning points. So we'll check that at the end, make sure it comes out to be true. Next, let's list our zeros. Notice that this graph goes up by increments of 1, but it's going down by increments of 2. So pay close attention when you're listing your values. Anyways, we have a 0 at -1, and you can see the graph turns at that point, so we're going to say that the multiplicity is 2. I mean, it comes up, it touches that point, and it heads back, so it turns at the value of x equals -1. X equals 1, multiplicity of 2. All right, if I write a potential function based on my zeros, I would write this as x plus 1 with a degree of 2 and x minus 1 with a degree of 2. I do have to recognize that my y-intercept occurs at 0, -2. So I need to test when x equals 0, and it needs to come out to -2. 0 plus 1 squared times 0 minus 1 squared. This ends up being 1 multiplied by 1, which is only equal to 1. So as of right now, this does not work. And our function, this function that we wrote, cannot be our final answer. So we need to make our y-intercept work. So what can we do to this value right here to get it to match our y-intercept, which is at -2? In other words, what can we multiply 1 by to make it equal to -2? And the answer to that would be multiply this by -2. That would give us the equation of 1 times -2, which is equal to -2. So our final function would be this function here multiplied by -2. And we're going to write that as f of x is equal to -2 multiplied by x plus 1 squared multiplied by x minus 1 squared. You want to double check and make sure that your degree matches. If we were to check our power function, we would multiply the first term of every factor, which would be -2 times x squared, which would end up being -2 times x to the 4th, which matches our minimum degree. So we are all set, and we know this is our final answer. And for this on your own section, I'm just going to bring the answers in from my website, and I'm just going to talk about them. All right, number 1, we're sketching the graph of the polynomial, and this polynomial here is given to us in factored form. So in order to determine the end behavior, you need to find the power function, which is when you multiply the first term of every expression. So we do need to pay attention to our exponents and either include the exponents or expand your factors. So what I'm doing right now is I'm writing my expanded function, meaning I'm not including any exponents. Right here, instead of writing x minus 1 squared, I wrote x minus 1 times x minus 1. And instead of writing x minus 2 squared, I have x minus 2 times x minus 2. All right, now I can multiply the first term of every factor to give me the power function of f of x is equal to x to the 6th plus, who cares, we don't care what the rest of it is, we just need that power function to tell us what our end behavior is. In this case, it's even degree, positive leading coefficient, so both ends of our graph face up. Over here, I determine my x-intercepts from my factors. With my x-intercepts, I indicate what the multiplicity tells me to do. So am I crossing at that point or am I turning? You can see I labeled all of those. Between each point, I find an additional point. This allows me to more accurately sketch the graph. I have my y-intercept at 0, 8. And for my final graph, I come down, I approach -2, I cross through that point, I come and hit my additional point, I come back up to -1 where I cross through, I make a turn somewhere, I hit my y-intercept, I come back down to +1 where I bounce, additional point, bounce again at +2, and my final graph faces up in both directions. Remember, this is a sketch, so at this point of my graph, it doesn't really matter what yours looks like. Yours could have come right towards that y-intercept and back down. That's fine. I just sketched this quick. That was the direction my pen was going in, so I needed to make sure I hit all the points. And for number 2, you're writing a polynomial function given the graph. So we're going to start by identifying that we have 3 turning points. That tells us we have to have at least a degree of 4. I identify my zeros, and the multiplicity at both of those zeros is 2 because the graph comes down and it bounces at each one of these points. I write my potential function as x plus 2 squared times x minus 1 squared. When I test my value of 0, which is my y-intercept, I know my y-intercept has to match at 0, 4, which it does, so I know that my final function is going to be x plus 2 in parentheses squared times x minus 1 squared.